All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another class. Still have some people trickling in here. Let's actually just jump right into it. Exciting class today, not necessarily from a theoretical perspective, but we're going to be doing a lot of examples, and it might be a little fun. It's going to be a little bit different from last class, where I ended up talking for most of the class. We're actually going to do a lot of stuff today, and hopefully the class participation is also high. You are going to want to practice these things. They can be, they're simple, but they're going to be deceptively simple, meaning you just watch me do it, it's going to seem like, oh, that's easy. Of course I can do that. But then when you have to do it yourself, you might have issues. So be sure to participate, try the problems when I ask you to try them. We actually have a lot of examples to get through. This is from a recent page. This is from the page that we were on yesterday. So I'll just do a small recap of that because it is going to be relevant towards the end of today's class. So we'll do that and then we'll talk about it. So we started looking at non-homogeneous linear differential equations. Everything I say about this, it does apply to second order differential equations. So that is our focus in this chapter, in chapter 3. Pretty much everything we're doing is with second order differential equations, linear equations. So only the second order is present. However, there are lots of things that I'm talking about that they do apply to higher orders as well. So I'll just tell you right off the bat, and that's going to save us a lot of time in chapter 4, where we are going to focus on things that are larger, higher order than second order. However, we discovered yesterday that whenever you have a non-homogeneous equation, like over here, where your function g is non-zero, or it's not identically 0, it's just some function other than 0. The solution has this form. The general solution will look like YH plus YP, where YH is the homogeneous solution and YP is a particular solution. So it's one particular solution, which means Y sub H solves the equation if you put 0 on the right side. And Y sub P is just one specific function that solves the equation with G on the right side. And so you can add one specific function and combine it with the homogeneous function, and that is going to, the homogeneous solution, and that is going to give you the general solution. So that is what you should have taken away from that last section here. The general solution to a non-homogeneous ODE, linear ODE, has this form. Now the first part, the YH, which is the C1, Y1 plus C2, Y2, blah, 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 we already know how to find that form, at least for second order, at minimum. And now what I essentially want to do in today's class is to kind of focus on ways that you can find this YP. So I gave some ideas as to the intuition behind why your solution should look like this. Whether or not you understand that is not really important at this point, actually. That would be more important for you to understand in a linear algebra class. However, we are going to talk about two main methods to actually find that YP. So finding the YH, I already taught you guys how to actually do that. Remember, for the second order, for a second order linear ODE, there are 3 cases based on when the characteristic has 2 distinct real solutions or 1 real solution or complex solutions. Now, how do we focus on the YP? That's what we're going to do today. 2 main methods. One is called variation of parameters, and this is a general method. This can work on, in theory, any non-homogeneous linear ODE. Then there's undetermined coefficients, and this is a little bit more restrictive because it cannot work on any non-homogeneous ODE. It works on specific types. And so when I actually talk about undetermined coefficients, I'll tell you specifically what kinds of ODEs that method can work on. Another very popular method to do this, but we're not going to cover, is the annihilator method. However, that method is equivalent to the method of undetermined coefficients. It only works on a select group of things. And so I don't want to waste time teaching you something that doesn't even work in general anyway, when I'm already teaching you a method that we know about. And specifically in our syllabus, undetermined coefficients is what is instructed that we teach, and your general final exam will assume that you know undetermined coefficients as opposed to the method of annihilators. And so you can have questions that will be specifically geared towards understanding the first method, the undetermined coefficients. Okay, so that's it. These two, I just want to emphasize, these two guys are methods for finding the YP, only finding a portion of this general solution. You still have to find the homogeneous portion to find the general solution. But finding that YP, for some random ODE, how can I find a specific function that solves that ODE when it's not homogeneous? Right? So that's what we are going to look at. And that leads us into first topic of today, variation of parameters. Okay, so again, this actually comes down to us guessing, hoping, wishing that the particular solution is going to be somewhat close to the homogeneous solution. So you might I just showed it here, but you might recall that the homogeneous solution looks like C1y1 plus C2y2, and we know that C1 and C2 are constants. So all variation of parameters does is say, oh, well, what if the C1 and C2 are not constants? What if we make them functions? And then we pretend that the YP looks like that. It's a function times the Y1 plus another function times the Y2. What could that get us, right? So that's kind of the assumption. So in variation of parameters, we're pretty much going to assume our YP has this form that is mentioned right here. So we're going to assume our YP looks like U1y1 plus U2y2 plus U3y3 plus ... all the way up to UNYN. And where the U's in this case, these guys are now functions, they're not constants. So you pretty much take the homogeneous solution and turn all the constant coefficients into function coefficients. And then we are going to try to find a solution that looks like that form. And remember, we have the existence and uniqueness theorem that tells us that there are only a specific number of solutions. So we're fine with that. Pretty much any one solution that we can find here is going to be fine. So if it's possible to find a solution in this form, that is going to be good enough. It will work. So there's no need to worry about, well, what if it doesn't look like this form? That's a non-issue at all. We are just going to pretend that the solution looks like this form, and then we're going to try to figure out what the functions U1, U2, all the way through UN, what do those functions have to actually be in order to get the particular solution of this form to actually work. And once it works, that's good enough because, you know, existence and uniqueness theorem, we can use that for a lot of things. So how do we actually go about getting that to work? Well, if we want this guy to work means it solves this ODE. Solving the ODE means if I take all its derivatives and plug it into the differential equation, then that equation is going to make sense. So that's what we're going to start doing. So we start by doing the first derivative, right? Because I'm going to plug it into the prime. Now, of course, here you're going to do the product rule for each term. So you're going to differentiate all the y's, leave the u's alone, plus you're going to differentiate all the u's and leave the y's alone. Now, again, because we only care about some particular function, we don't have to be as general as we can possibly be. What we do for to make our calculations a lot easier is we pretend that this side here, which is what I have in red here, is just 0, just to make it easier. So I assume that my functions aren't only functions that when placed in the YP will solve the ODE, but they're also functions such that they will make this equation equal 0, which seems like a very weird requirement. But again, once we can figure out functions that does this, we are fine. It seems very restrictive, but it turns out that we will actually be able to find functions that will have that property. They will be able to solve the ODE when we throw it in the YP, and at the same time, if I take all their derivatives, multiply by all the y's, and add them together, I will get 0. And so now our y prime only looks like the first part, the white part, and so we take the derivatives of that again. So to find the yp double prime, I take the derivative of all the y primes, leave the u's alone, plus leave the y primes alone, differentiate all the u's. And again, to make my life a little easier, assume that the u functions are ones that they will make this equation also equal to 0. So I can ignore this right side right here. And the first one, call that equation 1. The second one, call that equation 2. So right now, we're like throwing these guys away, but you're going to find that it's actually going to be very convenient to have them later on. So that's why, even though I'm throwing them away and pretending they're 0, I'm still keeping track of these equations, right? It's kind of like when you're like making soup and you know, if you're in the South people, you know, they can reuse chicken grease and do whatever. Okay, you guys get it. So we're throwing away stuff, but it's actually going to be useful for something else later. So you have to have the pot of what you put chicken grease. So every time you're frying chicken, you can go back and use the same old grease. Okay, so we keep doing this. We repeat this process, right? So I just keep going through finding derivatives. I'm throwing away the right side. Find the second derivative, throw away the right side. Find the third derivative, throw away the right side. Find the fourth derivative, throw away the right side. But every time I throw away one of these right sides, I name them a specific equation because I'm going to use them later on. So eventually I get down to the n minus first derivative, and it looks like this. And again, I'm going to throw away the right side. This is now the equation numbered n minus 1. And then at the nth derivative, which I'm going to replace, this I'm just going to call this EQ. So this one I'm not going to throw away. I'm actually just going to now start plugging these guys in. So I go back and all of these equations, all these derivatives that I did, so I'm go back and I'm going to plug all these guys into the original ODN. At this point, I'm going to get a huge mess, but we don't have to do it. I already typed out what the answer is going to look like. So I'm going to go back and I'm going to plug in all of those guys, the YP prime, the YP double prime, all the way up to the YN prime into this original equation right here. What that's going to look like is going to be something like this. You're going to have this huge monstrosity where I just have the white parts, which is the parts that I did not throw away, and this red part here, which is the last red part here. So I would have all of that equals to G. Now, of course, here, the U's are going to be common terms. I can factor them out. And you'll notice that each individual here is going to look like what the original equation looked like. However, it has the Y sub I in places of Y. Now, what you're going to realize is that all of those guys, I put the rule lines here. You're going to realize that all of those guys, they will actually be 0 because Y1 is a homogeneous solution. So this part is going to go off to 0. That part is going to go off to 0. This part is going to go off to 0. All parts in the middle are going to go off to 0 because the Y1 is a homogeneous solution, Y2 is a homogeneous solution, all the way up to Yn is a homogeneous solution. So those will all give us 0. So at the end of the day, I'm only left with this portion of the equation to worry about. Okay, so now that's what I do. I set that equation. This is the important equation for me to now solve, and that is what I'm going to call equation n, right? So this is now the nth equation. And now you're going to realize that all those equations that I threw away before, here I'm going to reach into the cupboard for the old pot of chicken grease and set up a system of equations here, right? So this is the last equation, equation n, and these were all the equations that I was throwing away while finding derivatives. So that forms a system of equations. Now you'll notice linear algebra comes to help us again. We can write this in matrix form. You'll notice I can group all the y's in a matrix here that will function as the coefficient matrix. And the U primes are the guys that I don't know. These are the guys I want to figure out. They're actually the unknowns. They form the solution matrix. Then on the constant matrix, you'll see that it goes all the way down. That shouldn't be a Bn, that should have been a G. It goes all the way down to G. And let me fix that in the main notes before I forget. Okay, so on the right side, you see 0, 0, 0, 0 going all the way down, except the last line, there's a G. So that's a G right here. And this is our matrix equation. Now, notice anything about the coefficient matrix of this system? What does this matrix remind you of, the coefficient matrix? For anyone who is paying attention. So remember, more class participation today. I'm not going to be talking the whole time, just to set things up. But I want you guys to actually chime in. Well, yes, it has a determinant because it's a square matrix, but more importantly, it reminds you of a specific determinant called the Wronskian. So the determinant of that is going to be the Wronskian, right? So that was the guy that we spoke about last time. So these are just some things you'll notice. The determinant of the coefficient of matrix above is the Wronskian. That's the guy that we looked at yesterday. On top of this, because the y1 through yn form a fundamental set of solutions, they are from the homogeneous solution, the determinant is non-zero, which means Kramer's rule says that there will be a unique solution for these guys. So while we are restricting ourselves a lot, it turns out that we're guaranteed to be able to find functions that will do whatever I just mentioned that they will do. I will be able to plug them into the ODE, to the YP, and it will solve the ODE. And at the same time, they are functions such that they'll make each of these equations 0, and then they'll make this final equation G. And you're like, wow, that's a very restrictive thing. I mean, geez, lower your standards, dude. But it turns out I didn't have to lower my standards because Kramer's rule actually tells me that it is possible to find such a set of functions. Now, you might not know what they are in the beginning, but it's definitely possible to find them. So it turns out I'm guaranteed to be able to find a unique set of U functions that will do this thing, or more specifically, a unique set of U prime functions that will do everything that I just asked my YP to be able to do. And more than that, Kramer's rule tells us exactly how to actually find these functions. It is just going to be the WI over W. It's going to be the Wronskian on the denominator, and in the numerator, it's going to just be what the Wronskian is if I replace the, and that was also supposed to be a G. If I replace the ith column with 0, 0, 0, 0, 0 all the way down to G, right? And that gives me WI when I find that determinant, which means each UI is going to be given by this integral. Now, at this point, that's not unique because there's going to be a constant of integration. But again, I just need one function that's going to be able to do this. So we can actually ignore the constants of integration. And let me fix that typo. Earlier, someone showed me another typo that I had made, but hopefully it's one that was actually clear. So where was it? I mean, it should be clear because like everywhere I was saying one thing and then that one typo said something else. I already corrected it. So in our lecture yesterday, right here, I put 0, but it actually should be non-zero. But of course, in every other place that I mentioned what I was doing, I said non-zero, but in this part, I forgot to type the non part. And I typed the number 0 here. So it's when the determinant is non-zero is when you have a linearly independent set of solutions. Anyway, that being said, let's move on. So had to fix that typo there. And so that's actually going to be what the U functions are. And so this leads to what we call the variation of parameters formula. Given a non-homogeneous ODE, where all of these guys are continuous on some open interval, then we can find a particular solution on that open interval that has this form where each of the coefficients are given by this integral. More specifically, our particular solution is this guy, right? And that is variation of parameters. The variation of parameters basically says we can find a particular solution by doing this combination here. Now, that is more general. And technically here I explained why we can ignore the arbitrary constants. We don't need them. Technically, these guys are all definite integrals where t naught is a fixed point in the open interval and t is the upper limit. And we're thinking of these integrals with the variable s, and that's not necessary for you to understand. However, what we do need to know is what this would look like specifically for a second order. So everything I was mentioning above works for general nth order ODEs. Let's actually water this down to a second order. So what does this mean for second order? Well, if I have y double prime plus p of t y prime plus q of t y equals g of t, our particular solution is going to be given by this. It's going to be y1 times the integral of w1 over w plus y2 times the integral of w2 over w. Seems pretty straightforward. I'll even do better. I'll actually flush out what these formulas are. Now, of course, our Wronskian, you might recall, looks like this. First row is y1, y2. Second row is y1 prime, y2 prime. Do that determinant, you get this expression. So you can actually plug that into that formula. And the w1 is what I'll get when I replace 0g in the 1 column. And then if I do that, I would get minus y2. W2 is if I put 0g in the 2 column, the second column, and that would leave me with, here's another typo. That would leave me with minus y2 times g, and W2 would actually be positive y1 times g, making a lot of typos. I typed all of this, and obviously there's a lot of notation going on here. So I'm missing a G from here. Okay, and that leads us with this formula, which there is no typo there, right? So for a second order linear differential equation, if you want to use variation of parameters to find the particular solution, you end up doing this formula here. Now, obviously the formula involves some integrals. Obviously the formula also involves you knowing what the homogeneous solutions are, but hey, we know how to find those already. And then I just do that. So that leads us to this summary right here. And for now, that's what we're going to need to know in order to do variation of parameters. So what you can do is you can actually take a screenshot of that, because we are going to be using that to do some examples. So I'll give you some time to actually take a screenshot of that. It's probably going to take too long if you write it down. Give you 5 seconds. 5, 4, 3, 2, 1. Okay, so that is going to be the formula that allows us to find a particular solution via a method called variation of parameters. And basically it's called variation of parameters because the C1, C2, C3, etc. are parameters. And if we allow them to be functions, it means they're allowed to vary. So the parameters are allowed to vary. And so we call it variation of parameters. We can have variation in the parameters. And it really boils down to that formula. Right? And how did we figure out that formula? Linear algebra is how we figured out that formula. Linear algebra, very important. So that is it. Now, once we know this formula, we can actually go in and find particular solutions to a bunch of differential equations. And in fact, just to make sure that we don't forget what it means to find a general solution, I'm going to ask us to specifically find a general solution to all of these guys here. And that's all you need to know for variation of parameters. Actually, this box is all you need to know for variation of parameters. Everything I was explaining at this point was how this box was derived. Finally, examples. All right, now, I suppose I can do the first example for you guys, and then you guys help me with the other two. All right, so here's the example, variation of parameters. I know that's what I want. Okay, so I'm going to do this one slowly. You guys can see how you would do a problem from start to finish. I'm also going to be writing down some of the things that I might be thinking or some of the steps that I'm going through, so you'll know how to follow along when you're doing things on your own. So I see this equation. Now, regardless of what method I'm going to use to find my particular solution, I do first need a homogeneous solution. So I am going to go in and do find YH. It's always the first thing you're going to do. So this of course leads us to a characteristic equation, r squared plus 1 equals 0, which means that my r is going to be plus or minus I, which means that my YH is going to be, hopefully you guys are mouthing along with this, but C1 cosine t plus C2 sine t. Okay? So that's it. That's my homogeneous solution. 2, now I'm going to actually need to find the Wronskian, right? Because that's a part of the formula. I will actually need to know how to find the Wronskian. Find W. So here, our Wronskian is just going to be y1, y2, y1 prime, y2 prime, which it doesn't matter who you pick as y1 and y2, but here I'm just going to pick the cosine to be the y1 and the sine to be the y2. So the Wronskian is going to be, in this case, cosine, sine. The derivative of cosine is minus sine. Derivative of sine is positive cosine. So the Wronskian is going to be cosine squared plus sine squared. So the Wronskian is just 1. Okay, that's awesome. And now that leads me to step 3. I'm going to plug into the variation of parameters formula. Use variation of parameters formula. To find YP. Now, this formula says that my YP is going to be given by minus y1 times the integral of y2 times g over w plus y2 times the integral of y1 times g over w. And in this case, my g is actually the tangent function. My g is tan x here. And of course, here, this is a range on x just to make sure that my tangent is defined and continuous. Because if it's not continuous, then we're actually not guaranteed to find a unique solution. This is something that I'm going to talk about like after the test. Like, why do we need continuity to find unique solutions and show you that you might not have that. So in this case, my g is tangent x. I found the y1 and y2. That's from here, right? So here I'm going to call this guy y1, and I'm calling this guy y2. So my homogeneous solution looks like C1y1 plus C2y2. Find the Wronskian, step 2. Step 3, use the variation of parameters formula. So now I'm just going to actually plug these guys in. So this means that my YP is going to be given by minus y1, my y1 was cosine, times the integral of y2, my y2 was sine, times g, which is tangent, divided by the Wronskian, which is 1. And this is actually dx, plus y2, which is sine, times the integral of y1, which is cosine, times g, which is tangent, over the Wronskian, which is 1. And I'm using cosine, I'm using t's. Did I use x before? Yeah, so that was a force of habit. These guys should be x's. And okay, there we go. Okay, question here. Why are there 2 variables, x and t? Oh, well, I just mentioned. There shouldn't be 2 variables. It's just force of habit. So sometimes we use x's. It turns out that in differential equations and in a lot of the applications, very often your independent variable is thought of as time. And so it's very common to use t when you're talking about differential equations, but it's not always, and sometimes you use other variables. So sometimes I just regress to writing t as my independent variable just out of force of habit, because like 99% of the time you're working with differential equations, you are thinking of your independent variable as time. So anyway, here, now we just literally do these integrals. So this is minus cosine. This will be the integral of sine squared over cosine, because I just rewrite my tangent as sine over cosine, plus sine times the integral of, this is just going to be sine, because if I write tangent as sine over cosine, the cosines are going to be canceled and I'd be left with sine. Now, if I want to find the first integral, I would just think of the sine squared as 1 minus cosine squared. And so this would leave me with the integral of secant minus cosine. Okay, so that's going to be the first one, and we have formulas for each of those, so we all remember that. We're very good at Calc 2 and Calc 1. Jhevon reminded us to look over all that stuff. So at this point, that's integral is easy enough. Here, the integral of sine x we know is minus cosine. And again, I can ignore the arbitrary constants. And so this here is going to be minus sine x cosine x. Just in case someone's going to point it out, we deliberately ignore the arbitrary constants. Now, in the first scenario, the integral of secant, all together now, do you remember? Yes, we do. Ln of absolute value of secant x plus tangent x. Integral of cosine is positive sine, so that's just minus sine. And so now we can actually multiply this out. I would get minus cosine x ln of secant x plus tangent x. And then here I would have minus cosine times minus sine. That would give me positive sine cosine, but then I subtract sine times cosine. And so that's my YP. So that's a particular solution. That guy is going to solve the non-homogeneous ODE. If I take this guy and find the second derivative and then add it to the original function, it will actually simplify to tangent x. We have just found a particular solution. How do you know that's a particular solution? Linear algebra tells me that's the particular solution. Okay. So that's actually your particular solution. So this leads us to step 4, if required. Find the general solution, which here it was required. The question did ask you to find the general solution. So recall that this is just y equals yh plus yp. So in this scenario, the general solution is c1 cosine x plus c2 sine x plus, or I could do minus, but of course, it's not actually going to matter because we know that a constant times a solution is automatically a solution. So whether you actually put the plus this function or the negative of this function, it doesn't actually matter. They will both solve the ODE. It's also worth mentioning that someone will get the opposite sign for YP if they choose their functions in a different order. So if you chose the sine to be Y1 and you chose the cosine to be Y2, then your Wronskian would have, these guys would have opposite signs. and then you would have this having a different sign potentially. But then you should realize that it's okay to have a different sign, because that just means I have a multiplicative constant of -1, which a constant times a solution is a solution. This is something that we learned yesterday. So that is our general solution, okay? So we went very slowly through that. Let's just run over it one more time. I have a non-homogeneous second order differential equation. I want to find the general solution. The process for doing that is to first find the homogeneous solution. Do that based on the three-part strategy that I gave you 2 classes ago now. Now, that's the first part. Then you're going to label those each component of that solution, y1, y2, y3, etc. Then you find the Wronskian of all these solutions. That's there. Then you plug into the variation of parameters formula. This is a formula that helps us find yp. So, and of course, at this point, you should have this memorized for second order. And it's pretty easy, I think, to memorize the general order as well, because it has a very poetic, has a very repetitive pattern. So it shouldn't be too hard for you to memorize that. So I plug into that formula. Of course, I'm going to have to calculate these integrals. At this point, we're going to be in Calc 2, so it shouldn't be a problem. We've all passed Calc 2, and so ultimately we'll get to this answer. Then to find the general solution, I'm just going to add the two, add the homogeneous solution to the particular solution I just found, and that gives me our general solution. So that is it. Any questions on the process? Okay, that being said, let's go. Let's run through an example together. Hopefully this one will be a little bit quicker. So let's go. What do we do? What do we do? First thing. YH, how do I find YH? What comes up? Characteristic equation, what is it here? Right, you're going to have r squared plus 4r plus 4 equals 0. What does that solve to become? So that actually factors to that, which means you have r equals -2 is a repeated root, which means your YH is you have a repeated root of r equals -2. What is the homogeneous solution? Right, C1e to the -2t, and we are doing t's here, so plus C2t e to the -2t. And we know that we multiply by that t by reduction of order principles. So that's our y, that's our solution. Now, of course, I'm going to consider these guys to be some particular component of the homogeneous solution. So call that y1 and call that y2. Now what? Find w. Your w is going to be e to the -2t, its derivative, t e to the -2t, and its derivative. And I'm going to multiply across this diagonal and subtract the product across that diagonal. So that will give me e to the -4t minus 2t e to the -4t plus 2t e to the -4t. So the Wronskian here is just e to the -4t. Okay, then what? formula. So at this point, you won't remember the formula. So I'll remind you here, our yp is going to be equal to minus y1 times the integral of y2 times g over w plus y2 times y1 times g over w. I'm going to plug into that formula. Our y1 was e to the minus 2t. Our y2 was t e to the minus 2t. Our g, what was g? T to the minus 2 e to the minus 2t. Our g is t to the minus 2 e to the minus 2t divided by the Wronskian, which was e to the minus 4t plus dt. Plus my y2, which is t e to the minus 2t times the integral of y1, which is e to the minus 2t times g, t minus 2 e to the minus 2t over the Wronskian, e to the minus 4t dt. Let's clean this up a bit. E to the minus 2 times e to the minus 2 is actually e to the minus 4, so those guys all cancel. Same thing would happen over here. So this actually simplifies into minus e to the minus 2t times the integral of 1 over t. And this becomes t e to the minus 2t times the integral of t to the minus 2. So now I would just do that. We know the integral of 1 over t, that's ln of absolute value of t. In this particular case, you can forget about the absolute value because your t is positive, but let's just leave it just because of good habits. It's potentially wrong to leave it out, so let's not just risk it. Here, I would just have t e to the minus 2t times the integral of this is going to be minus t to the minus 1. So this is minus e to the minus 2t ln, and this is minus e to the minus 2t. Now what you're going to realize is that this part here is actually a homogeneous solution. So I'm actually going to even ignore this part. And so take yp equals minus e to the minus 2t ln of t. Okay, so now that I have that, what do I do? Question here, it doesn't matter what the sign with that homogeneous solution. It's deeper than that, as we showed in last class. It doesn't matter what the sign of any solution is. A sign change is just a constant factor, right? If I say negative of something or positive of something, it's just me saying -1 times the thing or +1 times the thing. A constant times a solution is a solution. It really doesn't matter what the sign of any of these guys are, ultimately. I mean, if you have a specific application where you want the answer to be positive, then you can just change the answer to be positive at will, and it's not going to change. So here, now you find the general solution. Your y, remember your y is equal to yh plus yp. So this means the general solution is y equals, it was c1 e to the minus 2t plus c2t e to the minus 2t minus e to the minus 2t ln. And that solves the general solution of this non-homogeneous ODE. So the solution to this guy, what is a function y that will solve this guy in the most general form possible? It's that guy. Yes. If a homogeneous part shows up in a particular solution, you should ignore it, because then what you can do is this e to the minus 2t here would combine with that e to the minus 2t. You'll just have a different constant in front of it. So it's going to be absorbed into that anyway. So you can just ignore it. So if any terms of your homogeneous solution pop up in a particular solution, you want to actually ignore them. There's going to be a scenario where you can't completely ignore it, but you have to change it somehow. We'll get to that in a bit. But yeah, that's it. That's variation of parameters. Hopefully that wasn't so bad. I mean, me explaining the linear algebra behind it probably got some of you lost, but at the end of the day, when it comes to applying what we learned from linear algebra, it shouldn't be too bad. There are times when you will actually need to understand something about the concepts, and I'll mention when those times are, but here, this is not one of those times. There's no, I'm never gonna ask you a question, and you would not be asked a question on a final that has you, that requires you to have to understand the linear algebra derivation of the variation of parameters formula. You're never going to need to know that technically. I just, for the sake of completeness, I told you guys where the formula came from, but you don't need to know where the formula came from technically. If you want to know variation of parameters for what you'll need in this class, technically all you need to do is know that box right there. And then you just need to know, if I want to find a general solution, I have to add the homogeneous solution to the particular solution that comes from this formula. And that's that. Here's another one. So how are we feeling about variation of parameters so far? It seems like okay. Are we good? Anyone like totally lost? Have any questions? Like, let me address them now. Integrals are messy. Well, that's a Cal 2 problem. that's not a problem. That's not a problem for Jhevon to answer. But yes, the integrals can be messy, but they're not the messiest we've seen, to be honest. I think in general, the integrals that show up when you do something like a homogeneous first order ODE, those guys tend to be a lot messier. Like those guys, it's very usual to have like, you need a partial fractions or a trig sub or something like that. But yeah, integration is integration. Like you are expected to, whenever an integral shows up, you are expected to know all the Calc 2 methods to be able to deal with that integral. So yeah, if integrals is something, and I'm not directing this at the person who asked the question specifically, this is just a general direction. If integral is something that you are iffy on, you need to have that corrected before the test. You need to like go back and look over your integral techniques and all that good stuff. Incidentally, I'm also teaching Calc 2 this semester, and I did go over integration techniques a few lectures ago, where I spoke about a general approach to integrals. Based on what integral you see, how would you approach it, and actually do a lot of examples. Now, you probably don't want to watch all the lectures on integration because you won't have enough time, but you can get my notes from that class, and that will tell you everything you need to know about integration for this class. Anyway, moving on. Other than the complaints that integration can be messy and the formula might be a little bit too long, it seems everyone kind of understands what's going on. So let me just make quick work of this one as well. And we'll move on to the next topic. So boom, I have this non-homogeneous ODE. I want to find the general solution. Okay, this limit on t is just to make sure that the secant function is defined. So, so first thing I'm going to do is find the homogeneous solution. So r squared plus 9 equals 0. This means, and by the way, pro tip, remember, watching me doing math is very different from doing math on your own. This happens all the time to students where they'll be like, I get what's going on in class. It didn't seem that bad, but I get stuck on this homework problem, or I get stuck on this, or I get stuck on that. Often what happens there is the student is just passively watching me solve problems. And of course it looks easy when I'm solving the problem because I actually know what I'm doing. I actually know the topic well enough to teach it. So yeah, it's going to seem very streamlined when I'm doing it. However, for you to do it on your own, it's a very different experience. So even when I'm doing these examples on my own, you should be mentally trying to stay one step ahead of me. Try to figure out what I'm going to write before I actually write it down, and then pay attention to whether you actually guess the right thing or you guess the wrong thing. This is very important. So even if I don't slow down and ask you guys to do a step for me or do a step with me, you guys still should, while I'm writing down, try to stay like one step ahead of me. Try to say the answer like 1 or 2 seconds to yourself before you actually see me writing it down, okay? So now, did you recognize that that would have been the characteristic equation before I wrote it down? Do you know what the homogeneous solution is going to look like before I write it down? Because a lot of times after I write it down, hindsight is 20/20. If you see it after I've done it, it's going to make sense to you in retrospect. But to do it on your own without me showing you, it's actually a very different thing. So while I'm going to essentially do this example by myself and just have you guys watch me, it's very important that you take an active role in this process at all times. Even when I'm here doing it for you, you need to actively listen to me. You need to actively make guesses as to what is the next line to come. Okay. All right. So hopefully you saw that from this, the solution would be plus or minus 3i, which leads to a homogeneous solution of C1 cosine 3t plus C2 sine 3t. And I see that someone typed that into the comment section before I actually did it. So that's good. Okay, so that's our homogeneous solution. And arbitrarily, I'm just going to think of this guy as my y1 and that guy as my y2. It does not matter who I pick for which. Maybe I should state that earlier. It does not matter who you choose to be y1 versus y2. It doesn't matter. If someone chose the y1 to be the sine and the y2 to be the cosine, it's still fine. Because the only thing that's going to result in is a sign change, and we don't have to worry about sign changes because a constant times a solution is a solution. Okay, so arbitrarily I chose the cosine to be the y1 and the sine to be the y2. So now what I'm going to do is I'm going to find the Wronskian. The Wronskian is going to be cosine 3t. Below that, write the derivative of cosine 3t, sine 3t, differentiate the sine 3t. That is going to be 3 cosine squared 3t plus 3 sine squared 3t, which is 3. So yeah, Roberto guessed it was 3, and this is correct. So the Wronskian is 3. Now you're going to have to plug into that formula. So I'm going to have my yp is going to be equal to minus y1 integral of y2 times g. Like even it's if you just directly start plugging stuff in, there is still a potential for errors to happen. So even me, I like just writing down the formula really quickly before I start actually plugging these guys in. So my y1 and y2 are sine 3t, cosine 3t and sine 3t respectively. And my g, what was my g? 2 secant 3t. So this is cosine 3t integral of sine 3t times 2 secant 3t over 3 plus, let me move the chat box out the way. y2, which is sine 3t integral of cosine 3t times 2 secant 3t over 3. 2 secant 3t over 3. Yeah, so that's that. Now secant, remember, is just 1 over cosine. So this secant 3t here is actually, so I can think of this as minus 2/3 cosine 3t times the integral. The secant I can think of as 1 over cosine 3t, the secant 3t, and then sine 3t times 1 over cosine 3t. Well, that's just tangent of 3t. Plus, I have the secant, the sine 3t here. And I can factor out a 2/3. And I would have cosine 3t times 1 over cosine 3t, so that's just 1 dt. And so now 2/3 cosine 3t. The integral of tangent is ln of absolute value of secant. But here I have to divide through by a 3 because substitution is how I would actually integrate that. Integral of 1 is just going to be t. So this is 2/3 t sine 3t. So this is just minus 2 over 9 cosine 3t ln of secant 3t in absolute values plus 2/3 t sine 3t. And that is my YP. Now I just go and I plug these guys in. So this means the general solution is going to be C1 cosine 3t plus C2 sine 3t. And then I literally just copy this guy. And that is going to be the full answer. That is the general solution. Okay. So again, you want to solve something and you're thinking of variation of parameters. It's a non-homogeneous equation. First, find the homogeneous solution. Label individual components, y1, y2, etc. Find the Wronskian of these solutions. Then plug into the variation of parameters formula to find the YP. Once you do the integrals, you may have to ignore parts that look like the homogeneous solution. But once you're done with that, you just combine the YH with the YP, and that is going to give you the general solution. And that's it, guys. Variation of parameters. That's the method. And of course, variation of parameters really focuses on the YP, but you knowing that you have to add the YH to the YP to get the general solution is something that you knew when we talked about facts about solutions to ODEs. So that's another thing that you put together. But yeah, that's variation of parameters. This is why it works. This is the linear algebra behind the method. You don't need to know that though. You will need to know this formula for when we hit higher order differential equations in chapter 4. But for now, you just need to remember this formula over here for second order ODEs. And it comes down to applying those formulas in conjunction with finding the homogeneous solutions, which I taught you to do in a previous class. And that's that. That's variation of parameters. Now, I've listened to the people. Some people find that integration can be annoying, and it turns out that there are times when we can get to a particular solution without doing integration. Now, that leads to a whole other method. That leads to something called undetermined coefficients. So this is a method that allows us to find a particular solution in a different way, and it does not require integration. It doesn't require any integration formula. What it is going to require is differentiation, and it may require, although very often is the case, it may require setting up a system of linear equations and solving them. But so if you prefer that to doing a bunch of integrals, then undetermined coefficients is for you. Ask your doctor if undetermined coefficients is right for you. Okay, now it turns out that this method is a little bit more restrictive in the sense that it doesn't always work. For this method to work, undetermined coefficients, your equation and your G needs to look like a very specific form. Your G needs to be a solution, or sorry, not solution. Your G needs to be a function who is similar to its derivatives. So it has to be a function that when you keep differentiating it, you keep getting a similar function to what you had before. And it works very well when the coefficients on this side are actually constants, right? So while it's possible to make it work in general, it's easiest to work when you have constant coefficients on this side, and on that side, you have a function whose derivatives are similar to what the original function is. When you're in that situation, you can use the method of undetermined coefficients. And I'll explain to you why it's called undetermined coefficients in a little bit, but for now, let's get a little bit more specific. What do I mean by G is self-similar with its derivative? Well, that means G specifically is one of these classes of functions. It's either going to be a polynomial, or it's going to be a polynomial times a sine function, or it's going to be a polynomial times a cosine function, or a polynomial times an exponential function, or a polynomial times an exponential times a sine, or a polynomial times an exponential times a cosine. Or potentially, it can be a sum of a bunch of these different types of functions. So exponentials, as you know, when you differentiate them, you keep getting back the same exponential to the same power. You also would recognize that if you differentiate sines or cosines, you keep getting back sines and cosines. You'll also notice that if you differentiate a polynomial times an exponential times a sine, or a polynomial times an exponential times a cosine, the result is always going to be a polynomial times an exponential times a sine and cosine, right? So these guys here are actually self-similar with their derivatives. So this is the method that undetermined coefficients will work for. And this is, undetermined coefficients involves a little bit of guesswork on the front end, and this is required for your guesswork to actually be accurate. And it's much harder if the coefficients are not constants. So for us, I'm only going to ask you to use undetermined coefficients. If ever, I'm going to ask you to use it in a situation where you have constant coefficients on your linear differential equation, and your G, the right side, is a function of one of these types specifically. So it doesn't work in general. That being said, to look at a previous example that we just did, here, this is a tangent. I want you to appreciate that undetermined coefficients could not work on this example because that's a tangent. It's not one of the nice forms. Undetermined coefficients cannot work on this example. Why? It's not a polynomial times an exponential. If it was only an exponential, if it was only e to the minus 2t on this side, then we could do it. But with the t to the minus 2, we can't do it. With this one, that's a secant. Undetermined coefficients would not work on this example, right? So I just want you to appreciate all the examples that we just did for variation of parameters, undetermined coefficients would not have worked. So if you wanted to find a particular solution for one of those guys, you were pretty much stuck with something like variation of parameters. Undetermined coefficients work in these specific situations. It's very important that you know that. Now, it starts out by guessing the form of what your YP is, and you're going to figure out what it is afterwards. And so this table here will tell you how to make the guess, right? So that's what this table here that I typed up will tell you. Here's how you're going to make the guess when it comes to undetermined coefficients. What you're going to want to do is based on your G, you are going to want to find, based on your G, you are going to want to find the most generalized version of that type of function that will look like the G, but at the same time, it's not going to overlap with any part of your homogeneous function. So that is the trick. And so here, the t to the k that you're going to be seeing in this table repeatedly represents a function that you can multiply by to make it unsimilar to the homogeneous solution. And I'll talk about that in a little bit. Okay, but for now, let's just understand the kind of guesses that we're going to make, and then we'll go into a bunch of examples. And like I said, in this, we have lots of examples. Look at that, lots of examples. Because while the method is ultimately going to be simple, understanding how to do it in practice is going to require a lot of practice for you to be able to spot the right thing and set up the right equation. Okay, so suppose our function on the right is some nth degree polynomial, right? So in the above table, Q of n is just some specific nth degree polynomial. My P of n and my R of n is a general nth degree polynomial. This means you account for all powers counting up to the nth power, and you don't leave anyone out. T to the k is the smallest power of t that ensures that each term in the yp is different, linearly independent from the yh. Why would you multiply by t to the k? Well, remember we did reduction of order, and we showed that if we have two solutions that seem similar, you can multiply by a t to create a linearly independent solution, right? We're taking that same idea here. So here, g of t, suppose it's a polynomial. So some specific nth degree polynomial. Then my guess for yp would be the following. I'm going to guess that it looks like some general nth degree polynomial, where potentially I have to multiply by a t raised to the k to make it not look like any term of the homogeneous solution. And I'll explain that a little bit later. So here's a specific example. Suppose the right side looked like 2 minus t cubed. That is a specific third degree polynomial. My guess for yp would be a general third degree polynomial, which is at cubed plus bt squared plus ct plus d. I have to account for all powers. It is a general third degree polynomial. However, if any one of these guys here show up in my homogeneous solution, like maybe a t squared was in my homogeneous solution, I have to multiply by a power of t that was going to make that t squared not be a t squared anymore. I want no t squares to be present. And that's it, that would be the guess. Now, the name undetermined coefficients comes from the fact that these coefficients in the beginning are not determined. We don't know what they are in the beginning. They are undetermined coefficients. That's where the name comes from. Ultimately, to complete the method, you will need to figure out what the A, B, and C, and D must actually be. But in the beginning, in your initial guess, you have no idea what these numbers, what these constants are. But you just know this is going to be the general form. Multiplying by a t to k is not always necessary, but it might be necessary if there is overlap with your homogeneous solution. Here's another possibility. If your g looks like a polynomial times an exponential, a specific nth degree polynomial times an exponential, then your particular solution is going to be like a general nth degree polynomial times that exponential, potentially where you need to multiply by some power of t so that you don't have any overlaps with your homogeneous. Here's a specific example. Suppose the right side looks like t squared e to the 3t. That, you'll notice, is a second degree polynomial times the exponential. I'm going to put a general second degree polynomial times the exponential, at squared plus bt plus c times the exponential. Now, if my homogeneous solution has any of those terms, I'm going to keep multiplying by a t until it no longer has any of those terms. What if I have a polynomial times a sine, or a polynomial times a cosine? Then my general guess would look like this. Some general polynomial times a cosine plus some general polynomial times a sine. It's very important that you recognize when you have a sine or a cosine, you need to have both the sine and cosine in your general guess. And again, multiply by as many factors of t as I need to get to be different from my homogeneous. Specific example. Suppose on the right side I have t times sine 2t. This is a first degree polynomial times sine 2t, which means my guess should be a general first degree polynomial times cosine plus a general first degree polynomial times sine. So it looks like at plus b times the cosine plus a ct plus d times the sine. And potentially I have to multiply by a power of t to kill overlaps with the homogeneous, but not always. And that will be the general. the guess for the YP. Now again, I can have a polynomial times an exponential times a sine or a cosine, and the guess would look like this. General polynomial times the exponential times the cosine plus general polynomial times the exponential times the sine. We're multiplying by a power of t just in case to kill the overlap. So now, specific example. Let's say your right side looks like t e to the 2t cosine 3t. Then your guess for the YP is going to look like at plus b e to the 2t cosine 3t plus ct plus d e to the 2t sine 3t. And potentially I multiply it by a t to the k. And so that's the process of how to guess what the form of YP looks like. Okay. Now, of course, I kind of asked the question for you here. Jhevon, what do you mean by t to the k is the smallest power of this? So right? It's a question that I ask all the time. I know it's going to come up at some point, so I just decided to be preemptive and answer it before. I explained to you why multiplying by a t actually fixes the situation. And it's just basically take the intuition from what we did with reduction of order. Once I found e to the t was one solution, multiplying by t to get a t to the t gave me the second solution in a repeated root case. So you can apply this idea more generally here, right? So here's a specific example, right? And it's not just choosing based on this table, but your choice will depend on what your homogeneous solution looks like also. So even if you're doing undetermined coefficients or variation of parameters, it does not matter. You need to know what your homogeneous solution looks like in its entirety. So suppose your guess was something like this, a e to the 2t, but your homogeneous solution looks like this, c1 e to the 2t plus c2 e to the 3t. Notice that here, the c1 e to the 2t is exactly the same form as a e to the 2t. They are not linearly independent. It's a constant times e to the 2t for both of them. So we would amend our guess. Instead of guessing a e to the 2t, I would guess a t e to the 2t. Multiply by a t is good enough to make it not dependent with my YH. And so now it would look like a G, but it's not going to look like the YH. Here's another example. Suppose the initial guess was AE to the 3T, and you realize that your homogeneous solution came from a repeated root scenario where it looks like C1 e to the 3T plus C2 T e to the 3T. So now what I would do is multiply this by T to kill overlaps. It's not going to overlap with the first term, but then I'd realize, oh wait, now it overlaps with the second term. So I'd have to multiply by T again. So ultimately I would change my guess to AT squared e to the 2T. In this case, I'd have to choose K equals 2 because that is the power I need to make it not overlap with any term in my homogeneous. So if I just multiply by a T, it's not good enough because it overlaps with this term. Or if I multiply just by, or if I keep it originally, it overlaps with this term. So I multiply by enough T's, as many T's as I would need to kill all overlaps. Okay, so that's the idea. Hopefully that is clear, but even if it's not, we are going to do a ton of examples where we practice this sort of thing. So hopefully that's clear. But what's in red here is the important thing. Our YP must look like G, but not like YH. So we need to choose something that's going to look like G. How do I know it's going to look like G? Well, I'm going to choose according to this table over here. If my G looks like something on the left, my guess is going to be something on the right. At the same time, I do not want any terms to overlap with my homogeneous solution. If there are any overlaps, I will keep multiplying by T until there are no longer any overlaps. Okay, that's basically it. That's how we would do the guesswork for YP. Now, in general, we're not going to be done after that. In general, we would need to be able to find what is the A, B, and C's in my guess, right? I'll need to actually know that in order to fully answer a question. So here's the process, the method of undetermined coefficients. Here's what a full breakdown of the method would look like, right? So step one, guess YP using the table above, right? So I have a non-homogeneous Od E, and it's very convenient to use the method, right? So what does it mean that it's a convenient to use the method. So let me be specific here. Coefficients are constants. And G has the form and G has one of the forms. In the left column of the above table. Or a sum of such forms. So once you look at an ODE and you notice that the coefficients are all constants and my G is of one of the forms in the table, meaning it's a polynomial, or it's a polynomial times an exponential, or it's a polynomial times an exponential times a trig function, which is a sine or a cosine, or it's a polynomial times a trig function, which is a sine or a cosine specifically, right? So assuming that I'm looking at something that looks like that, the method of undetermined coefficients is doable. And step one is to just make the guess. Make the guess based on how I told you to make the guess in this table. Step two is if it's required. It's not always required. There are times where I'm going to just ask you for the general form of the particular solution without having you actually solve for the specific particular solution. So if it's required, you can find all the coefficients by, well, actually finding all the derivatives of your guess and plugging them into the differential equation. What you're going to realize then, after you simplify the left side, is that you'll be able to match up functions on the right and the left. You'll be able to equate coefficients. And then you can set up a system of equations to solve for the coefficients. So that is the general method. And of course, it goes without saying that I said it here more generally, and this is, again, going to save us a lot of time when we get to chapter 4. But the method is unchanged if it's a second order, right? So we're going to do practice with some second orders here, but the principle is going to be the same for higher orders as well. So let's actually jump into some examples. So again, let me do the first one. I will have you guys help me with some of the others. Okay, so we're going to end this class with going through a bunch of examples. All right, so here's the method from start to end. Again, first thing I'm going to do, find homogeneous solution, find YH. So this comes to r squared plus 4r plus 3 equals 0. I believe that factors r plus 1, r plus 3. This means that my r equals -1, or my r equals r equals 3. R equals -3, which means my homogeneous solution is going to look like C1 e to the minus t plus C2 e to the minus 3t. Now, in this first example, in example 1, I don't care about the arbitrary coefficients, the a, b's, and the c's. I just want you to tell me the general guess. So now, step 2, guess yp. So now here, my g, here, g equals e to the t. It's just an exponential. In fact, it's a 0-degree polynomial times an exponential. So my guess is going to be yp equals some general 0-degree polynomial times that exponential. Now I'm going to go back, check there is no overlap with YH. So I look up here. Does any of these guys look like a constant times e to the t? The answer is no. Nah, we good. Right? So that's your yp. A e to the t would be the guess here. Now, yes, in general, you'd have to figure out what that A is when required, but for this particular example, I just want you to get practice on guessing what the form would look like. And so for this, that's what we're doing. Now, in general, we'd have to continue. And we'll see how later. But not for this example. All right, and that's it. Hopefully that wasn't so bad, but let me see if it was bad, and you guys let me know. This example, what do we do? In fact, the first part here is very similar to what I had here. So we have the homogeneous solution already. So I already actually did that for you. We know YH equals C1e to the minus t plus C2e to the minus 3t. All right, someone guess what my YP would look like. What's your guess for YP? Right, I would guess AE to the minus t, right? But now we go, hold up. There's an overlap here. That is also a constant times e to the minus t, which means my yp prime, my yp is not good enough. It overlaps with a homogeneous. So this means I would multiply by a t. And then again, check for overlap. In the above. So I go back, does anyone look like a te to the minus t? Nope. So at this point, you're like, we good. And that's going to be the guess. Are we getting it? Okay, awesome. All right, go. What do we do? Find YH. How do I find it? What is it here? R equals plus or minus 1? No. You would have r squared plus 1 equals 0, which means your r is going to be plus or minus I, which means your YH is cosine and sine. And again, I'm going as a force of habit writing t's. In this case, it's an x. So now I would guess my YP. My YP, what is my YP going to look like here? See if we understand at this point. What would it look like? No. And don't put t to the k. Be very specific. I'm asking for the answer here. Right. ax plus b e to the x is going to be the guess. Then I would check overlap. I'd realize we're good. And so that is the answer. Or the answer to this example. That is the guess that I would make. It looks like ax plus b e to the x. How come? Well, my g is x e to the x, which means my g looks like this form in the table. My g is a q sub n e to the at, which means my guess should look like this. Right? Here, my g is a first degree polynomial times an exponential. My yp should look like that, a first degree polynomial times an exponential. The guess is to make sure that the form you're guessing for the particular looks like the form that's on the right side. Yeah, it's a method that it works well in the scenarios where it works. It's much more efficient. Now, obviously, we're not actually doing the full problem here, but I want you to know how to guess, because I know there are going to be some confusion, even though we might not realize there are. So I'm just running through a bunch of examples. Here's another example. It's actually quite similar. At least the left side is. We saw YH was C1 cosine X plus C2 sine X. So, all right, let's see a guess here. Maybe Insha, what would you guess here? No. Why are you guys putting threes? Remember what the table says. You want a general polynomial. It's called undetermined coefficients because you don't know what the coefficients are going to be. If you tell me 3 cosine x plus 3 sine x, you just determined the coefficients. You don't know what they are. It has to be a generic coefficient. Okay, your second guess is closer, but not quite. So this is what we want to make sure we understand this table. Look over here. If I have a polynomial times a sine or a cosine, and I'm guessing, notice that I have Pn of the cosine plus Rn of the sine, which means I cannot assume that the coefficients are going to be exactly the same polynomial. I want to address the fact that they could be different polynomials, which means a cosine x plus b sine x, correct? So that is going to be my initial guess. I wrote the cosine before this. Are we getting it? Why that would be the initial guess? So the initial guess starts out by just trying to get something to look like the G. So here, this is a first degree polynomial times sine. So my guess is going to be a first degree polynomial times cosine plus a 0th degree, 0th. So my guess is it's going to be a 0 degree polynomial times cosine plus a 0 degree polynomial times sine, where these guys have to be generic and general. I do not know what the a and the b are going to be. So I can't guess that they're 3 right off the bat or 5 or anything else. I also cannot guess that they're going to be the same number. They are undetermined coefficients. I don't know what they are. I don't know that both of these have to be a's, or you know what I mean? So here, it's just an a that is going to represent some constant that is going to work on the cosine part, and a b is some other constant that is going to work on the sine part. Initially, I don't know what these guys are. Right, and Jason realizes, hey, that's a problem. So now when you realize, if you check overlap, you realize code red. There is a problem. This is exactly like that. That's the same, right? As far as linear independence is concerned, it's the same thing. My homogeneous is a constant times cosine plus a constant times sine. And the guess that we just made is a constant times cosine plus a constant times sine. My particular solution cannot be the homogeneous solution. It has to be distinct. It has to be different. It has to be linearly independent. So at this point, what do? As Jason mentioned, you multiply by x. And so yp is going to look like ax cosine x plus bx sine x. And that's what the form of my particular solution should look like. Okay. This is good. We're finding a lot of the common mistakes that would show up here, which is good. We want to find all of those before the test. So let's actually make sure that we understand everything. Here's another example. And in fact, these are all very similar. So I'll let you guys work on all these. So what we'll do is we'll do these 3 examples. They're all very similar. The left side is the same in all of them. And what I will also do is we'll end there. I'll leave these guys for you guys to actually try. So technically you should be responsible. You should know how to do all of these because I told you everything you need to know how to do all of these for the test. So our test will cover everything up to what we did today. So you need to know everything from the beginning to undetermined coefficients and how to fully solve a problem. But I'll leave these guys for you to try because 1, we're out of time, and 2, I really want you guys to try by yourself to actually solve these problems. And so you can figure out what errors you might have, and we can actually deal with them tomorrow. So we'll go over these tomorrow. I'll leave these in the PDF version of the notes so you can actually practice. But for now, what I would like to do, I'm going to give you guys 5 minutes to find the answers for all of these. It's very similar because the left side is the same, but do this on your own. 5 minutes actually probably too much, but whatever. Do this on your own and then we'll go through it. I'll move some of the others down in case you guys actually, some of you are able to solve it in fewer than 5 minutes. You can try your hand at these guys. So if you already got through all the answers, which if you got the first answer already, the other two answers should be very quick. So potentially you already have it solved. Then move on to the next problem. One minute left. All right, hopefully you guys tried that. And you all have answers, what you think the answer is. Hopefully you weren't just waiting around for 5 minutes to see what I would do, because you're putting yourself at a disadvantage. Anyway, all right, let's move on. Let's actually look at these. So I already see some guesses in the comments in the chat box, but we'll see. So here, hopefully you did something like this. First, you want to find the homogeneous solution. So that comes down to solving this quadratic. You should realize that that would factor into a perfect square. This means that you get r equals 1 as a repeated root, which means that your YH is going to be C1 e to the t plus C2 t e to the t. So this means that my YP is going to be, well, I look at the original. My original is A e to the t. because that looks like a 0-degree polynomial times the right side. But then I check overlaps. So then I look and I see that in my YH, there's a C1 e to the t. So I multiply by a t to kill that overlap. Let me actually write this one out a little bit better. So overlaps with this, so multiply by t. And so then you would get yp is equal to at e to the t. Then you check again, and now you realize that it overlaps with this part now. So multiply by t again. And so now I would end up with yp equals at squared e to the t. And no more overlaps. So that is your guess. Now, of course, you don't have to write out everything that I'm writing down here. I'm just trying to explain to you guys what I am doing while I'm doing it. Now, the moment you have this line, you should immediately be able to write down this line, right? But I'm just kind of showing you with the thought process that I'm going through here. So I start out by making it look like the G, but then I check for overlaps. Once I find an overlap, multiply by t, check for overlaps again. Find another overlap, multiply by t again, check for overlaps. I keep multiplying by t until there are no more overlaps. In this case, I had to multiply by t twice. So that's what the t to the k meant in the table that I had before. In this case, k is 2. I had to multiply by t twice in order to actually kill all the overlaps. And so here I look overlap with the first term, multiply by t. Now I overlap with the second term, so I multiply by t again. Now I overlap with none of the terms. So that is the proper guess for yp. Now, if I look at this guy, so hopefully people got that. So let's see. So no, some people got it wrong. Did anyone get it right who typed it in the comments? No. Apparently everyone who typed it in the comments got it wrong. But it's good that we find that out now than we find that out on Friday. So let's be grateful that we're wrong now when it doesn't matter. And hopefully we'll get things straightened out. So now notice that the left side looks just like the left side here. So the homogeneous solution is going to be the same. So notice that this looks like YH equals C1 e to the t plus C2 t e to the t found earlier. So I'm not going to show you how to find that again. Now I do my initial guess, YP. My G is a first degree polynomial times an exponential. So my initial guess is going to look like this, AT plus B e to the t. Now I notice that there's overlap with the t e to the t. And it overlaps with the AT, the C1 e to the t. So if I multiply by t, I would get a t squared and a t here. I need to multiply by t squared to kill all overlaps. So here, my YP would look like AT cubed plus BT squared e to the t. If I expand that, I have a t cubed times an e to the t and a t squared times an e to the t, which doesn't overlap with any guys here. If I only multiplied by a t, then when I expanded, I would have gotten a bt e to the t, which would overlap with the second term, which is why I had to multiply by a t squared. So this is what your YP should look like for example F. Did anyone get that? F? No, we were still off in F. No, we're still off. Yeah, Incha retried F and got it correct. But everyone else messed up. Like I said, don't feel too bad. It's better that you know that you messed up now than messing up on Friday. So hopefully you're seeing how the process fits together, and you need to actually do more practice for later. So here, again, very similar. Here, this YH, you guys can do a final initial guess for this one in light of what we did earlier and see if you got it. And hopefully, if you got it wrong earlier, you can end the class on a win. You can actually get it right. So here we have C1 e to the t plus C2 t e to the t. Okay, maybe I'll give you guys another like 10 seconds to write down what the answer is going to look like. If you actually understand, it should be enough. And just something for the future, technically it's not incorrect to do this, but I would leave it in factored form. So some of you are writing out the correct answers, but you actually expanded the parentheses. I would not do that. Because remember, ultimately, we're going to want to be taking derivatives of this thing. So if you expand it, you're going to have to do the product rule multiple times as opposed to just one time. Not sure what Eugene is typing in the comments. Poly is not specific enough. Also, the polynomial should not be squared. Okay, so let's see. So I would first start by making it look like the right side. AT squared plus BT plus C. That's how it all begins. Then I realized that these two terms overlap. So I multiply by a T. And then I'd realize that this term overlaps. So I'd multiply by a T again. And so ultimately my YP should look like AT to the fourth plus BT cubed plus CT squared e to the T. And that is the correct guess. Right, and someone in the comments got it. E to the 4, BTQ, CT squared. And Incha, your answer is also correct for G. However, like I said, I wouldn't expand it. Leave it like this. Because now, if I want to take a derivative of this, which I'm going to need to do eventually, I just have to use the product rule once. By expanding it, you have to apply the product rule 3 times. It's just going to be a lot messier. Right, so the initial leg of undetermined coefficients is a lot easier than variation of parameters. However, you just need to realize that once you start taking derivatives and plug it back in, the algebra can get a little bit messy. So what you want to do is you want to keep things in as a contracted form as possible, so that once you start plugging back in, you don't have like this huge algebraic mess to deal with. You have things that are a little bit more neatly packaged. So leave it in factored form. That is the correct YP. Also, I would mention that if you multiply by any power of t that's higher than 2, that can also work. But again, it will make it needlessly complicated. So just multiply by the smallest power you need to actually get it to work out. And that's going to be good enough. Now, these guys we will go through tomorrow. However, you should be able to do all of them. So I'll put this here, leave this here. You mean, could you, for the last example? No, you still need the C term for the last example. Because you have to have a general quadratic, right? So it's a t squared e to the t. So you should have 3 terms in your polynomial part. To answer the question on the general, no. Ultimately, you are going to need to find what the A, B, and C are. And yes, the roles, the A, B, and C are generic constants. It doesn't actually matter how you write the letters. Like I could write C t fourth plus a t cubed plus b t squared. It's not going to matter. I'm going to solve for these numbers at the end anyway. They're arbitrary constants. However, if you're doing this out of order, I don't know why you would not go in alphabetical order. It's weird, but mathematically it's not wrong. But why would you count the alphabet in the other way? I don't know. So it's not wrong, but that's more straightforward. A, B, C, D, D. Okay, so that's that. So try these problems for next time. Make sure you get that. Here's a problem. Technically, I have not taught you about higher order coefficients, but in principle, you actually know everything you need to know to be able to solve this. So try that one for tomorrow as well, but if you don't get it, don't feel too bad. And this is a full problem. So this problem here, this one problem here, puts together a lot of stuff. It puts together applying an initial condition. So we're going to need to find the C1 and C2 from our homogeneous solution. You have to do this after finding your particular solution, though. So I'll mention that because that would be a common mistake that students can make. You must find general solution before finding C1, C2. So make sure that the moment you get the homogeneous solution, it's very tempting to start solving for C1 and C2 right there. That would actually be incorrect. So you do need to you do need to make sure that you find the general solution first, which means first find the YP completely, identify all the coefficients. Then once you have the general solution, YH plus that YP, you plug in the initial conditions and solve for the C1, C2. Finding the coefficients of the homogeneous solution is always the last step in the process. Okay, I'll make sure that the sample tests on the class webpage are open. I will also look into that. And yeah, we'll stop there. We'll wrap up there, guys. Hopefully that was understandable. Yeah, that's where we're going to end it there. And I will see you guys in the next one. That's it. Go study and good luck on Friday. I will see you guys tomorrow. Try those problems for tomorrow. And I guess I'll see you in the